yellow foray. I hope you are well rested. Even puppies need a nap after learning KMP. Logarithmic abilities are flowering. Heralding a new week. Welcome back.
As Sir David Attenborough wished, I hope that you are well rested, that you're feeling excited about some more algorithms. Your assignment is out, meaning that you have a chance to really go out and practice all the things you've been learning so far, and also learn a bit more C. And then we'll get to some more exciting algorithms as class goes on. I've also lined up a really exciting guest speaker for us for the last week or the second last week of class, exact date TBD. And so we should have a chance to learn about large language models, neural networks, and ChatGPT, which I know for many of you is front and center of mind. So, as always, we begin the week with one of our historical figures. This is Barbara Liskov, who is one of the pioneering women in the last century in computer science. She is the 2008 winner of the Turing Award and was the second ever woman to win the Turing Award. However, her path to greatness in computer science was not quite straightforward. In fact, when she completed her undergraduate studies and went to do a PhD, Princeton denied her a space in their mathematics program, citing that they don't accept women. So unfortunately, she was forced to go to another institution whose name I won't speak too loudly, Stanford, where she eventually completed a PhD on distributed computing. And as part of her work, she came up with the notion of a particular theoretical notion of data abstraction, something that we are very familiar with and we study in this class. And this led later down the line to object-oriented programming, a subject that if you complete FOA, many of you will go on to take in subsequent semesters. So with that, we're back to our regular content. And so I want someone who I haven't spoken to before, with blonde hair.
Oliver.
Oliver. Okay. What's your name?
Oliver.
Okay. How old are you?
19.
And where are you from?
Auckland.
Auckland, New Zealand? Awesome. So we have a person who's composed of here, his name was Oliver. And he's composed of a couple of different attributes. Now we could represent these attributes a few different ways and see what are some ways that, I'll ask you, Oliver, what are some ways that you could put all this information about you into a C program?
You can make structure.
Ooh, that's getting a little ahead of things. Okay, let's pretend that we don't know what that is yet. So what are we going to do? How are we going to put this information into our C program?
You could do it in a lot of ways. You could make an array.
Okay, so we could have an array, and what would the first element of the array be?
My name.
And the second element?
My age, but as a string.
And the third element?
Another string, that's where I'm from.
And what about if we want to put in your grades? Like, say you got a 60 in vector calculus. Is that too low? Should it be 75? Higher? Higher or lower?
A little higher.
Okay.
Yeah, you could write it just as a string.
Okay, but we're running into a bit of a problem here, and that's that our array only has data of one type. And also we'd have to keep track of, okay, the 0th element is the name, the first element is how old you are, and the third is where you're from. So now let's say we have two students, Oliver and behind Oliver, what's your name in the glasses? Yep. Ray? Blake. Okay, so now we've got Oliver and Blake. And Oliver, now what's a way that we could represent both of your information? Without, we're not going to say the S word, but...
Okay. Another way to represent the information.
Yeah, so we've now got two students. How could we represent both students' information in our program?
Make another array.
Okay, so we could have two arrays, one for each student. Or maybe we could have one array per piece of information that we're trying to keep track of. So we could have a name array that keeps a name for all of our students. We could have an age array that keeps the age of all our students, and the where are you from array that keeps track of all the places you're from. And in fact, we can do this pretty easily. Okay, so this is a program where I've done the same thing, except instead of for students, I've done it for planets. So planets have a whole bunch of different attributes. They have names, orbits, distances, masses, and radii. And you can see up the top there, let me zoom in on that a little more. I've set the array to be able to contain max planets, where max planets is 2, so I'm only going to have 2 planets in this array. And then I have declared, when I've created the array, I've given them a whole bunch of attributes, and then I can index through each of the arrays, keep track of where in the planets I'm up to, and then print them. So this is one way of doing it. But it's starting to get a little annoying. Every time I want to add an attribute to the planets, I'm going to have to create a whole new array, and then I also have to keep track of what planet we're up to, and then index into this array, index into that array, index to the next one. So we probably want something a little more robust that is easier to modify, because now let's say that our students start taking an additional class, or they go on study abroad, and I want to have the location that they're going on study abroad as well. I want to be able to just quickly modify the student data without having to have a whole new array to keep track of. So this is where we get the S word. And what was the S word? Structs. So this is a whole new way of representing data that refers to a coherent idea. So just like students might have a whole bunch of different properties, you could imagine a whole bunch of things in the real world have properties. So if you have an animal, it could be the animal type, it could be the number of legs, it could be the size, it has tail or doesn't have tail, you could have a Boolean. And this is going to be a new paradigm for abstraction again. We're going to take the object that we're thinking of, whether it's a digital object or a real world object, we're going to come up with a list of properties that it has, and then we're going to be able to create instances of this particular object. And you'll learn a lot more about this kind of paradigm in the object-oriented programming class that we discussed earlier. But C does have facilities for actually working with objects that have more than one property. So instead of just being int age equals 5, int age 2 equals 7, int age 3 equals 15, etc., we can now associate it with a whole bunch of other properties. So let's see how to do this. So here I have my planets program again. And now, instead of just having this a large set of arrays, I'm going to use this funny syntax to declare a struct. Now what I'm doing with this typedef here is, remember, a typedef just allows us to make a variable's name another name. So if we want to remember the data t type that we've been using, so we can easily switch out what is data t. So in this case, we're going to switch out what is planet t. And planet t is going to be this thing. So all we're doing is calling this thing planet t. That's why we use the word typedef. You can make a struct without the word typedef, but typedef just makes it easier to refer to, because then we don't have to use the word struct everywhere. So this is going to be our planet t type. So we declare it, we say typedef struct. We open with curly parens and close with curly parens, and in here we're going to put all the different types of properties that we want our struct to have. So as before, in our array version, we're going to give our planet a name. We're going to give it something that it orbits. Planets typically orbit around stars. Or we could have moons that orbit around planets. We're going to have the distance from the star, the mass, and the radius, all of which are doubles. And then we can declare them using this syntax. So we have the planet t, which is just a type like any other type, except what type is it? It's a struct. And because it's a struct, and we've declared it earlier, this particular struct, a planet t struct, is going to look like this. C also allows us to use this syntax for initializing a new variable of this type. So we have our planet t type, and in order, we have the Earth, which is the name, orbits the sun, distance is 149.6 million kilometers from the sun, its mass is 5.9 times 10 to the 24. This syntax is also likely going to be a bit new to you. This is just a way to represent scientific notation in C. So you can imagine that as being 10 times 10 to the power of 24. But the way we write that in C is just with this E plus notation. So it is 5.9 times 10 to the 24 kilos, and its radius is 6,700 kilometers. Then we can do the same for the moon, even though the moon isn't technically a planet, but it's going to orbit around the Earth, and we fill in all the details. What we can also do is we can create another planet, but not initialize it. So this is just like creating a variable, but not setting all its properties. So if we were to go and check what properties another planet has set, it would just be uninitialized junk data, whatever was in the computer's memory before, whereas if we checked the name of the Earth, we would get Earth. So great, we've created these objects. Now how do we actually access the properties? So let's go through our main function. So in our main function, we're going to create a new planet. Our planet is going to be equal to copy struct, and we'll see what that does in a minute. Then we're going to print the planet, and we're going to do some other stuff with it that we'll see shortly. Okay, so let's look at print planet. That's probably the easiest function to understand. So we have 4 printf statements, one for each of the properties that we're going to want to print out, because if you look up the top, we've got 5 properties, but we might not want to print them all. So, we do print out all 5 here, because one of the print statements has 2. So the first thing we're going to do is print the name and print what it orbits. So we have a normal printf statement. It takes in a string and then another string. And what we're going to do is we're going to go to the argument of the print planet function, which is one planet, and we're going to access its name. And the way we access its name for a struct is just with a dot. So this is planet.name. Then we also want to print out what it orbits, likewise with all the other properties. Okay, seems relatively straightforward. But what we did before printing it, we actually have to fill this planet in with some stuff. So how do we do this? This allows us to use scanf to fill out all the details of the planet. So copy struct creates a new planet. It says enter all the details of the planet, and then takes in all the different values. And you'll notice here that we have had to add ampersand signs to get the addresses of these. Why don't we need an ampersand for the name or for orbits? They're already pointers? Who said that? That was Eugene. Eugene said they're strings, and so what do we know about strings? They end with a 0 byte, but why can we just use them in scanf right away? Why do I not need to put an ampersand? Yeah?
Because they point towards the pointer.
Yeah, because a string is really a pointer. It's a fancy way of doing a pointer that points to a set of memory. And so in this case, we don't need the ampersand out the front when we're reading in a string from scanf, because we're already talking about an address. We're already giving scanf the address. Okay. Let's give this a run, and then we'll return to this bit after. Let's create a terminal. And compile it. This was struct.c. There we go. Enter name, orbits, distance, mass, radius. Okay, I need some values. Well, what am I waiting for? Mr. Pivot. What does Mr. Pivot orbit? 49.2, great. Okay, so Mr. Pivot orbits me. Its orbital distance is 2 million Ks. It weighs 0.75 kilos. Radius is 4.9 kilometers. Okay, now we do this again. Let's put in the same details. Prints the same thing. But let's pay a little closer attention to what's happening. So in our first call to copy struct, let's go to copy struct again, and let's look at its return type. Copy struct is returning a struct. So this is quite convenient. Remember how in C we can only return one thing at a time from a function? This is another way of returning multiple things, because you can have a struct that contains a whole bunch of different properties, and yet we're able to return it. So what we did inside copy struct is we created a new planet, we filled out its details, and then returned it. And then our compiler is clever enough. when we've returned a whole struct from it and set a new struct equal to the return value, it's copied all the data that was returned into the new struct. It's assigned each of the properties correctly. Now let's take a look at pointer struct, and this time we're giving it the address of planet. Let's see what's happening here. Okay, pointer struct is returning an int and takes in a pointer to a planet. And remember, this is a pointer to a struct because planet T is a struct type. We type-defed it earlier to make it refer to something different. So we've done the same thing, only this time we're not using the dot notation. This arrow notation over here is syntactic sugar for both dereferencing and accessing a struct property at the same time. So instead of having to write something like that, so dereference the planet, and then once you've dereferenced the planet, get its property, we have this syntactic sugar, which is just a fancier way of writing it, that allows us to go directly to the property. So this is dereference planet, and then access its name. And now we're using scanf and reading it directly into the input struct, the struct that was copied over. Now, why does this work? Remember, C is passed by value. So haven't I just copied something over that's not going to be accessible in the main function? What's going on here? Why might this work? Joseph.
Me? Okay.
Yeah, you.
Is it because you're accessing the actual memory?
So that's correct. What did I pass into the function?
A pointer to planet.
Yeah, I pass in a pointer to planet. And what is a pointer to planet? Just give me another way of saying that. You kind of said it before.
It gives a memory value?
It's a memory address. So what we've passed into the function is a memory address. We've copied that address, and we've said this address refers to a planet T struct. And so when I set each of the values, I'm actually setting the memory address, something that refers to the memory address that was copied over into this function, which actually points somewhere outside of the function. So when the function gets destroyed, the things that I've modified were elsewhere. They were actually in the main function's memory. So we can see here that we declared the planet over there, and then we passed in the address of that planet, the planet that is active in the main function. So then when we print planet over here, all we're doing is again passing around the planet that's been filled out by our pointer struct version. That'll take probably a little time of playing around with to get used to it, the difference between passing a struct and passing a pointer to a struct, but we've still got some more questions about like why would even bother doing this that seems a little complicated. In fact, structs allowed us to get around the limitation of functions only returning one thing. Why would we go back and make it more complicated? So this gives us to the question is, should we use plain structs as arguments to functions, or should we use pointers to structs as arguments to functions? So this here is actually part of the Linux kernel, Linux being an operating system, and this is all one struct. And I'm scrolling, and I'm scrolling, and this is one struct. Look how many properties it has. It's still going. This is one struct. I'm not sure we have time to look through the whole struct. Oh, there we go. No, it's not going to finish. Look, this struct goes practically forever. And so it seems like this is an awfully big thing to be copying and moving around every time. Remember, C is passed by value. So if every time I want to use this struct inside a different function, I give it as an argument to that new function, I'm going to be copying this. We're still going. I'm going to be copying this really, really giant struct over, and then when I run another function with this struct, I'm going to copy it over again. And this is going to A, use up a lot of the computer's memory, and B, also potentially be quite time-consuming. Oh my God. See what I mean? There we go. We've finally gotten to the bottom of that struct. That struct ended over there. That is the end of the task struct. So structs are just too big to pass around willy-nilly. There will be instances where it's appropriate to do it, but given how much memory structs take up, it's going to be much more sensible to pass pointers to structs. So we just have the struct located in one place in memory, and then we're going to refer to it using pointers. So let's go to our student example. This is a pointer to a student. And as I said before, we're going to use this notation now to refer to dereferencing the pointer and then accessing one of its properties. So just as we did before. So method one for creating a struct pointer, we could do roughly as follows. So we have our function that takes in a pointer to a student t, and I've then created the normal struct the normal way without the star, and then I've created a pointer to it just by taking its address. So the same as you would for any other variable, it's no different for structs. Method two for creating a struct pointer. So now I can create the pointer ahead of time before I've even set aside memory for it. And now I'm doing something kind of funny here. I've got this weird looking statement and a cast. Remember how we could do casting? We could convert variables from one type to another. So whatever this malloc function is doing, I'm converting its output to be a student t pointer. Now, again, Joseph, remind me, what is a student t pointer?
It is a pointer that accesses the memory address of the struct.
So a pointer should contain a memory address, which is a number, right? And so if I'm assuming that I've coded my thing correctly, this function malloc, what should it return? Just the type. Well, what type should malloc return?
Student. Sorry, student?
Well, this is student. It's not returning a student because over here, this is not a student. That's a pointer. And a pointer is you said it before.
Right. So an int?
A pointer is a memory address, which is just a number. So it should be giving us back a number. And if this is being sensible, that number should be an address. And if we're being really sensible about this, well, we want this number to refer to a chunk of memory that we can use as a student. Because you can see here that I have a student pointer. I'm trying to convert this into a pointer to a student. So what I'm looking for is for this malloc function to give me a chunk of memory that I can use as a student. Oscar, you had a question.
Oh, that's right. I was just going to ask, so does it depend on which system you're using? Like, will malloc return like just a 32-bit int, or will it return a 64-bit?
So we'll get to how malloc works in a second. For now, we're just trying to understand what we're hoping that this function does before even actually opening up the box. Okay, so let's assume that malloc has given us a chunk of memory that we're going to be able to use as a student. So what we've done here is we've actually told the computer from now on, whatever that chunk of memory was, treat it as if it is a pointer to a student. And then what we can do is we can start using it. So let's say we want to copy a string. I can copy some strings into my student that I've now set aside some memory for. And I can set the age, and then I can print it as before. So assuming that I've got this right, I now have a chunk of memory that I can use, and I can start moving things into that chunk of memory in order to actually treat it as if it was a student. So what is our malloc function doing in this whole instance? Malloc is asking the computer to give us a chunk of memory that we can later use for whatever we like. And in this case, we were asking for a chunk of memory that we can use as a student. Now, one of the key things that we need to do is we have to tell the computer how much memory we want, because it doesn't know right off the bat. We're going to have to give it the size, or the size of the chunk that we want. So let's open up our terminal over here. And when we don't know how a function works, we have a technique for figuring it out, and that is the man pages. So let's go man malloc. So we can see inside this page of the manual, there are a whole bunch of different functions that we could use. Let's start with malloc. So in order to use malloc, we're going to need to include the standard library up top. Now let's scroll a little bit. Okay, the malloc functions all allocate memory. The allocated memory, blah, 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 blah. The malloc function allocates size bytes of memory and returns a pointer to the allocated memory. So this is roughly what we saw in our example before. We ask malloc, we give malloc the amount of memory we want, and it gives us back a pointer to that chunk of memory. And the other one let's look at here, the free function deallocates the memory allocated to by a pointer. So this will also come in handy. So return values, if successful, they return a pointer to the allocated memory. If there is an error, they return a null pointer. So how can I check if malloc has succeeded? Oscar? Yeah, so you run the malloc function, you get a pointer back. If that pointer ends up being a null pointer, then you know that it hasn't succeeded. Okay, and then if you want to, you can go read about how to debug things when stuff goes wrong. That's all in the man pages. This is a particularly good man page to read if you're looking for some enrichment and for maybe some tips that'll help you make your programming life a little easier. So the man pages can be a little complicated, but they're always a good place to check out, even if you're just beginning as a new computer science student, because the more and more stuff you read about this kind of thing, you'll get more sophisticated over time, and you'll start picking up, as you learn a concept later, you'll think back, oh, I remember reading in the man pages that there was this thing, and now I can connect the two concepts. So I'd encourage you, when you're learning computer science, to push yourself with content that might not make sense to you to read it the first time. Go ahead, read it anyway. Might not make sense, but later on, you'll have been exposed to those concepts. So later, when you go and learn it, the pieces will start to fit together. And this generally goes for learning in your university career in general. It's a good idea not to just restrict yourself to the course content, as long as you're doing all right in the class. It's a good idea to try and piece together a few pieces that are a little more complicated, because eventually the concepts will mesh. Okay, so where does malloc give us this memory? We've answered what it does. If we look in our figure that you've seen now a whole bunch of times in the class, if we look at the text here, dynamic memory allocation through malloc, free, and delete, although we don't have free and delete in, we don't have new and delete in C there from C++. So if we do malloc, the computer is going to give us memory in this heap area over here. Where has all our memory been so far, Belle? When we create a new variable, where have our variables been going?
I don't know.
Don't remember? Okay, someone else? Oscar, you've already answered a bunch. Emmeline? Yeah, they go on the stack. And so we put them on the stack. The stack goes down and down and down and down as we start filling things up. And if we put things on the heap, then the heap builds up and up and up and up. And now you can get an idea of where all the different types of variables are going to be put and why we actually have this heap. We separate the heap from the stack so that we have separate regions that we can use to put things in memory. Because if we start mixing up the stack and the heap, we're going to not be able to grow the stack very easily, because we'll have to work around the things that were malloced on there. So the basic idea here is that when you use malloc, you're going to save a chunk of the heap for the computer, for your program to use, and the amount that you've asked for is what you'll get. So malloc allocates memory on the heap, and you get back a pointer to the memory that was allocated, but we have to give it back when we're done. It wouldn't be nice to the other programs on the computer if we just kept mallocing things, and even when we're done with them, we just leave them there. So the right thing to do is to free it at the end. And what you do is you run the free command, you give it the pointer to the memory that you were given, and you say, I'm done with this. And then the computer gives it back to the operating system. Now, has anyone ever used a web browser and opened a few hundred tabs and then had to restart their computer before? Hands up if that's happened to you, where your computer kind of stops running. So this is probably an example of what's called a memory leak. And a memory leak is roughly as bad as it sounds. It means that the program has been forgetting to free things. And web browsers have been historically pretty bad about this. I remember Chrome used to do it quite a lot. That somewhere in Chrome's million lines of code, someone has forgotten to add a free that matches one of their mallocs. And the more you use the browser, the more that line of code is going to allocate things, and eventually your computer's going to run out of memory, everything slows down, it's having to shift things around in order to find just a tiny bit more memory for you to do things, and so you give up, you hard reset the computer, Chrome dies, and you're free. So this is a lesson in why you should be better programmers than the Chrome ones, even though they did a relatively good job overall. And always match your mallocs with frees. And we'll give you some tools and tips to how to make sure you're doing this later on. We do have a bonus operator as well. This is an addition to our pluses, our minuses, our double pluses, our equals, all of our operators that we've already learned already. This is the size of operator. Now, I'm looking for the biggest genius in the class who can tell me what the size of operator does. Bronson. Big brain Bronson?
Yeah, I think it probably gives you the size of the,
He is a certified genius. You feed in an object into the size of operator, and it tells you what the size is. However, there is a catch. Sizeof is not going to be able to tell you the size of things that are dynamically allocated. So if you've used Malloc to set aside a chunk, sizeof isn't always going to be able to tell you how large that chunk is. There are a whole bunch of conditions here and there where sizeof will and won't work. Don't worry about those for the most part, but the problem is that the thing that you have to remember is that you should be using sizeof only on simple types in C. So if you want to get how large is an integer in C, how many bytes does an integer use up, then you can use sizeof. If you want to get how large is a struct, how many bytes of memory does a struct take up, then you can use it. If you want to use sizeof on an array, that's when you start running into trouble. It is possible in some instances to get sizeof to give you the correct size of an array, but do not rely on it. Just use sizeof for basic types. If you're interested and want to extend yourself and are not trying to get an H1 in the class, then I would encourage you to learn about all the edge cases where sizeof will and won't work. But for the most part, for the purposes of our course, just use sizeof on the basic types. Don't use it on arrays. Don't use it on pointers because you will get burned. What does sizeof do? It just gives us an unsigned int. So this is only a 0 or positive number, and it tells us how large the type is that we're looking at. Sizeof can be a little clever though, so you can give it a variable instead of a type. And if that variable's type is a simple type, like an int, then it will be able to tell you how large it is. But again, discourage you from using it. Just use it for sizeof with a type. So it does not work on arrays once they've been passed around. So if you want to toy that out, create a function with an array, pass the array into the function, try to use sizeof, you'll get the wrong answer. Okay, so back to our code. What we've added now is we now know what our Malloc does over here. We are getting the size of a student, and then at the end, we are freeing the memory. Now, one other catch. Notice that at where I'm allocating the memory over here, I'm using, what type am I using? What's my return type from Malloc in this case, or what am I casting it to? Joseph, you said before?
The student struct? Or no?
It's not a student struct. It's the memory address of a student struct, which is a student t pointer type. However, when I'm using sizeof, I don't want to know how large a pointer to a student is. I want to know how large a student is. So that's why for the first half of that line on the left-hand side, I'm using the star because I want to, Malloc is going to give me back a memory address, and so I want to deal with a memory address. But how much memory should I get? How much memory should I get just refers to the size of a normal student, not how large is a pointer to a student. A pointer to a student is just going to be as large as a pointer is. All our pointers are going to be the same size. We don't want to allocate space for a pointer. We want to allocate space for a student and use that as a pointer. And those two concepts are different. So remember, the left-hand side of the Malloc is going to look different from our argument to the first sizeof. Now, structs are also quite powerful in that we can nest structs within structs. So for example, a student might take many, fill in the blank, student might take many classes, and each class the student will receive a grade. And so then we might want to, and each class also has a course code, and it has an instructor, hopefully, otherwise I don't know what I'm doing here. And so we might want to have structs within our struct, or even better, we might want to have a pointer to a struct within a struct. Because the student might have, you might have a list inside the student of, you might want to have a list, sorry, of all the different classes they're taking. And so inside the student, I'll have an array, and the array will be an array of pointers, and it'll be an array of pointers to classes. And so then you can go inside the student, and then you can loop through all the elements in the student's class array, and each of those classes will point to a struct elsewhere that will be give all the details of that class. And so in this way, we can start composing all the different ways we have to represent data inside one another to give us complex relationships between them. What does this look like? You can see inside our task struct, this was the Linux giant struct that I showed you before. The very first thing inside it is another struct. called thread info. And so we are nesting a thread information struct inside a task struct. And then here's the definition for our thread info struct. It's a struct like any other. Don't have to worry about these particular things. But this is essentially what makes your computer run, is a series of complicated structs which keep track of all the programs running inside the computer. So one thing I want to do is I want to actually show you what happens if we pass around giant structs instead of passing the pointers to the structs. So here I've made a demo called slow struct. And what I've done here is I have some code that just calculates how long bits of my code run for. So I start a clock and I stop a clock. In this one, I'm doing the copying version, where I'm passing the whole struct around, and then in the second version, I'm doing the pointer struct, where I'm just copying the pointer. Let's see what it does. And I am doing 1 times 10 to the 8 copies in each instance. So I'm doing 1 times 10 to the 8 copies of the whole struct, and then 1 times 10 to the 8 copies of just the pointer. So the one that where I was copying it, it took 0.29 seconds and copied, how many is this? That is 4 billion bytes. And in the second one, you can see we shaved a chunk off of it by copying an order of magnitude fewer bytes. And I could do, let's do 10. Do it again. And leave that to run for a second. That'll take about 20 seconds. So let me take 1 order of magnitude off of that. That should give us some good results. There we go. So you can see we're getting a sizable savings, even though we're doing this on a relatively small struct. This is just for a planet struct, which has only 5 elements. And already we see a pretty notable difference between the version where I'm copying the struct and the one where I'm copying the pointer. My next one, I have our full student objects finally. Oops. So here I have a student T, and a student T has an array of subjects within it. And the array of subjects is an array of subject structs. So you can have an array of structs. What is a subject T? A subject T has a subject code, a final mark, scores for all the assessments, and how many assessments there are. And then I have a struct for date. I have a struct for a full name of a student. And so in this case, you can see I've composed my student T out of a whole bunch of nested structs within it. And I have some code that prints within the student. It can print student.name, which is a struct, and then name.given to get the given name. So in this way, I can go down the different levels of nesting just by using a dot each time, which is a fairly convenient syntax to refer to what otherwise would have been arrays on arrays on arrays on arrays to represent all these things. So how am I actually going to use this? Let's say we have 500 students in FOA. We're now down to about 455. Do we have a Vincent in the class? I don't remember a Vincent. So let's replace, because I know we have Jessica. I don't think that last name is right, but we will live with it. Okay, so date of birth. What year are all of you born? Roughly? 2004? Okay, so let's make this a little more realistic. And now we can have the scores in Comp 101. Got an 89 in 101 and did not do as well in FOA, was not coming to class enough. Okay, and then we can have a second student. And then once we have the 2 students that we've made, we can then go through and print all the students that are allocated to our FOA array. So let's run this code. nested.c. And after a few fancy print statements, you can see Jessica van Vanderbilt with this funny ID, born in 2003, prints out all the various details from all our sequence of nested structs. Now I will put this code online for you. I think the link probably works. Let me try the link. So there are a whole bunch of reasons why we might decide to use structs. It's just one other tool in our C toolbox. It's not one that you have to use. Your programmers, it's up to you to find the best way to represent your problem and your data. So why might we use these? Structs are really good for bookkeeping. You store like information with like other information. So just like you have all the details for a student, you want to keep them together instead of putting them in different arrays. Here's a benefit. They're flexible. You can return multiple things from a function at once. It's easier to maintain code that way, and it allows us to have hierarchies like we saw in that last demo, where you have FOA is a class. Inside the class you have students. Inside the students you have a name. A name has a first name, a last name, and a middle name, or all the different elements of the students that we saw. There are a few limitations to structs though. So one thing is that it doesn't necessarily make that much sense to compare a struct directly. Like if I ask who is the biggest student, Jamie or Evan, it's unclear what I mean by bigger in a programming context. I mean, you could say bigger means size. You could say bigger means whoever got the better score in FOA. You could say bigger is whoever's name comes first in the alphabet. This is not a well-defined question. So you can't say, are these two students equal, or is this student bigger to another student? Because we haven't actually told C what these notions mean. Now, in some programming languages, there is a way to tell the programming language, this is what I mean by comparison, this is what I mean by equality, but C doesn't have this. So you're going to have to write your own functions that you can then use to compare things if you actually want to be able to say, sort students by age or sort them by first name or last name. So structs are quite useful in a number of different contexts. They are similar to arrays in that they can store multiple things. However, arrays are for storing the same type of information over and over and over and over, and structs are for storing what is like conceptually the same kind of object. And so you should think about them in slightly different ways, and in choosing when to use them, ask yourself, am I just storing a list of the same thing over and over and over and over, or am I trying to add structure to something that I could reasonably conceptualize as an object with lots of different properties? So if we go to one of the slides from our review deck, here is a comparison between arrays and structs. We can assign elements of an array directly. We can't do that for structs. We're going to have to write a function that copies each bit of the struct to each bit of the other struct, except when we're using it as a return value. Arrays, you can do comparisons. So if you compare if two arrays are equal, what does that normally do? If I say array A and array B, array equals B, what am I comparing? Yeah.
The memory address?
Yeah, you're comparing the memory address. So that's actually going to work in C. That doesn't tell you whether the contents are the same, but it tells you whether they're the same array. You can't do that for structs. Structs, you're going to have to rely, if you want to check if they're the same struct, you could get the address of both of the structs and compare the addresses, but you can't compare them directly. You can use both of them as arguments to functions. You can return both from functions, but in the case of arrays, you have to use pointers. You can't take the array of an address because an array variable is already an address. And you can use arrays as pointers directly, but you can't use structs as pointers because even though structs have a memory address, you'd have to get that memory address by using the ampersand. So our overall message from this is that we now have more powerful tools for abstraction. When we want to abstract out how different parts of the program run the execution of the program, we're going to abstract things out into functions. And when we want to abstract out data, when we want to group data together, we can use structs as our form of abstraction, or one of our other tools like arrays, or even some of our fancier data structures, which we will cover in the remainder of class. And we will wrap it up for today. And a reminder that right after class, right now, we have the launch of the first year center with the donut wall, with the lunch, with the prizes. So please do come along. I'll be walking over as soon as I've packed up. Third floor of Melbourne Connect, there'll be signs, and there'll be hopefully like fun, fancy things to help point your way there. And with that, thank you very much for today, and it is lovely to see you all again.